Okay, let's see. Do this one again. Representation, and then final influence object. Okay, so June 17, okay, we will have a final in-class programming exam. So all you have to do is actually please bring your laptop, and in a laptop, of course, you have to install R, and then you have to download all Pharma French data, right? It's actually daily frequency, and bring at least 3 stop times each, right? Google, IBM, PND, something like that. Okay. And yeah. Okay, it doesn't have to be. If you download Pharma French frequency daily frequency, it is better for you to download daily data for start. If you want to use weekly data, it is fine. And then I will give you my.
The Pharma French data is in form of monthly.
I think they have daily data as well. Please check French webpage. They have daily data. So you get a simple in the blackboard. I will write down control question like do WS statistics, compute WS statistics, something like that. Do GLS, something like that. Then all you have to do is just do.
Can I use Korean data?
Korean data, yes. Then you need Korean Pharma French data, which is also easy to get. Any question? So it'll be fun, okay? So as Soe, I think Soe know how to do R, but also you have to do with P. Okay, so if you make a mistake like Soe did today, then you will never be able to solve the problem. I guarantee. Okay, so you need practice.
So if we can do every homework we already gave us and read, we agree.
Yes. Yes, of course.
Can we read other materials?
Yes, please. Yes. And of course, in the in-class exam, the problem will be small variation of homework. Okay, so it will not be same to homework, but mastery homework will necessarily condition to solve the problems. Okay. And still use regression errors and construct use this one and calculate this one. So it is not difficult. Okay. So everything you use is just a regression error from OLS. So collect regression error from OLS and calculate variance, and the variance should be A square plus B square. And you calculate correlation, they should be AB. So you know this one and this one, so you can calculate A and B. Okay. And of course we impose assumption that sigma x1 square is 1. Okay, because we have 3 unknown and we have only 2 equations, so we need one more restriction on the And actually, there are much easier way to calculate, to estimate model and serial correlation, which is this. So our model looks like yt equal xt beta plus epsilon t, right? And we multiply rho each side and give one rank, and rho yt minus 1 equals xt minus 1 beta plus epsilon t minus 1. Right? And then if we subtract this one from this one, we have yt minus rho yt minus t equals xt minus rho xt minus 1 beta plus epsilon t minus rho epsilon t minus 1. But given our assumption, this one should be equal to ET. Right? And then next, we can move this one over here and separate this and simply run the regression, then we estimate every time. Right?
And that equation is from the second line.
So it's a combination of
4 is not multiplied.
So okay, we have this one. By giving rank and multiply row, we have this one. And subtract this from this one. So this minus this, we have this one. And this error term should be this one. Given our assumption of AR1 error. And once we have this one, we move this one over here and separate these two. Then we have 1, 2, 3, 3 independent variables and run just OLS. Okay? Then we estimate everything. Right? Which is much easier than our Cochrane procedure. Next one is simultaneous equation. Okay. Yes, simultaneous equation. So first, big picture. So far, the most critical assumption we have made is that the explanatory variables are uncorrelated with error. So in particular, suppose we have this one, y equal x beta plus epsilon. We have assumed until now, we assume this x and epsilon are uncorrelated. The cross product of E x prime epsilon is 0. Or more precisely, that P probability limit of T x prime epsilon over T is equal to 0. Okay? But if this is not true, so it was our assumption until now. But if it is not true, then basically our OLS breaks down seriously. Okay? So if we do the OLS regression, basically our best head looks like this. And if we put expectation over here, then this term is not 0. So it's bit better. Head really different from that. That becomes unbiased estimate. Okay. So basically, because of this term, there is a serious difference, okay, deviation of our estimate from the true parameter. So that correlation between this error term and explanatory variable is one of the most serious problems in the regression. Okay. And whenever I write a paper, this is actually the most serious concern for everybody. So we need some techniques to get over this. First one is instrument vector variables, and we can use 2 or 3 stage least square. Or we can use limited to full information like maximum likelihood estimator. Okay. So it is no longer obvious that we can even estimate more of the parameters. This is called the identification issue. Okay, so we can explain this better with an example. So suppose we have this one, this example. So C equal alpha plus beta yt plus epsilon t. So CT, you can get CT is consumption. YT is like income, okay? Y income, okay? So regression equation 1 means consumption is linear function of income. Right? Linear function of income. Did you take macroeconomic class? 거시경이냐? Macroeconomic class. Please raise your hand if you took the class. Macroeconomics is important, so I recommend you to take it. But anyway, in the macroeconomic, you use the Keynesian consumption model. And more Chicago type model, like permanent income hypothesis, says that consumption should be functional wealth, not income. So anyway, it's Keynesian argument. And then of course income, okay? Actually, so it is consumption, so income, or you can, in that macro, if you regard those variables like macroeconomic variables, you can regard this as a consumption and this one as a GDP. And GDP is maybe, to simplify GDP is sum of consumption and investment. Of course, you need government condition and others, but let's assume, for simplicity, that GDP equals consumption and investment. And interestingly, there is no error term, right? There is no error term because it is just identity. Right? GDP is sum of consumption plus investment plus government expansion and international trade, right? That's just definition, identity. So there is no error term. So anyway, equation 2 is called identity because there is no error. Equation 1 and 2 together are the structure of the model, right? The structure model says that, okay, our GDP is sum of consumption and investment, and consumption is linear function of GDP, like Keynesian line. Okay? Then our goal is to estimate parameter of this one. And together 1 and 2, it is called the structure of the model, or it is called the structural equation. And CT, YT are the endogenous variables. They are called the endogenous variables because they are determined within the model. Okay. But C and Y are determined from endogenous. Right? C is function of Y, Y is function of this one. Right? They are determined within the model. So they are endogenous model. On the other hand, 1, so it is coefficient for this one. Actually, it is data for this. So 1. Constant term, and these investments and these error terms are called exogenous variables. Exogenous variables because they are determined outside of the model. So it comes from somewhere else. Okay. And then of course 1 and YT, okay, 1 and YT are explanatory variables in equation 1. Okay. We call 1 as an explanatory variable and YT as an endogenous explanatory variables. Therefore. And if CTI1, okay, so it is consumption 1 period ago. If we have information about consumption 1 period ago, or in the model, it would be a predetermined variable. Predetermined variable, but not exogenous. But for simplicity, I mean, it's a predetermined variable. However, rational for exogenous variable holds for predetermined variable as well. So for our statistical problem, we can regard predetermined variable kind of exogenous variable as well. Because it is determined 1 year ago, and today it is given exogenous. Now, so one obvious idea to estimate this model is to run regression, rigorous CT over YT, right? So that is one obvious idea, but that doesn't work in this frame because YT and epsilon, these two are correlated, right? In our regression, we always assume that these explanatory variable and error shouldn't be correlated, right? But if we use this structural model, they are now correlated. Okay, because there is correlation between Y and epsilon because epsilon T will affect CT, right? Epsilon T will affect CT, and CT will affect YT. Therefore, epsilon t will affect yt. Right. So since epsilon t will affect yt, they are not independent. They are not uncorrelated anymore. They are correlated. Thus, it is incorrect to assume they are zero. And in the model, okay, they are already said as they are correlated. So therefore, OLS estimate or even GLS will be biased and inconsistent. Okay. And on the other hand, instead we may be able to write, okay, we can plug this one, C plus IT into here, right? We can plug this one here. So CT becomes like this, and by solving this, we can express CT looks like this. Okay, once we get a CT like this, and we can plug this one over here, we can express YT equals something like this. Now we have regression equation such that CT and YT endogenous variables are all explained with exogenous variables at IT. And these are called reduced form equation because each endogenous variable is written as function of only exogenous variables and structural parameters like this. Okay? So we can write them as this like a linear equation such that phi 1 0 phi 1 2 0 all looks like this. And the reduced form parameter for error term looks like this. Reduced to error. Okay. So maybe we can run the regression with this. Okay. Note that in this example, there are many restrictions, but simply running regression is actually not because there are in the model, if we take into account the original model, this even this reduced form includes many theoretical restrictions. Okay. So note that in this example, there are many restrictions placed for the reduced form parameters and errors. For example, pi 1 0 should be equal to pi 2 0 by the theoretical experiment, and pi 1 and pi 2 1 should be better. Also note that we can estimate the reduced form parameters with OLS consistently because there are no exogenous variables. Okay, so basically we can learn OLS about the reduced form, and then solve for structural parameters. Okay. Although there are many ways to perform this second step because they over-identify restriction, which means that our restriction and then our OLS parameters are there is no one-to-one relationship. We have more restriction than that. So there are over-identified restrictions, and anyway, this method of estimation, so transform structural model into the reduced form and run the OLS for reduced form is called indirect least squares, so ILS. ILS properties are alpha beta are consistent estimation. It's natural because error terms and then our independent variables are now uncorrelated with each other, so they become consistent again, but they are actually biased. We will discuss it later. They are biased, but at least they are constantly useful. And alpha hat beta are not necessarily unique. That's the problem because of all the over-identifying restriction. So if we run regression and this we estimate this parameter, so which equation, depending on which equation we use, we will get different alpha and beta. So that's the problem. So alpha and beta are not unique because of that more restriction than the parameter, which is over-identified. So anyway, suppose we run OLS. On the equation 1, and if we use our formula for OLS, so then per hat would be, so is this figure, this term is deviation from mean. Right? So our OLS beta looks like this. Y squiggle is squiggle over y squiggle square. And we plug C squiggle, so C is, so because C looks like this, so C looks like this, so we calculate deviation from limit, then C squared becomes just beta squared plus S squared. Right? So we put this value over here. Okay, then we have this one. Then we multiply this and this. We have beta and we have this one. So we have this one. Right? And since we know y squared equal to this one by our reduced form regression, so we plug this one over here, y over here. Then we have equation looks like this. And again we multiply epsilon inside and we calculate square term of this one. And we have this low mass equation. And then if we simplify, we have this one. Okay. So once we have this one, now let's take a look at what will be the probability limit of this equation. So this probability limit, okay, probability limit of beta is becomes this one. So we need to calculate probability limit of this one, like this. And then next we divide nominator, denominator, both of them with t, right? Size of data, and we have this for t. And we can, by the property of Philip, we can put Philip inside of everything. So we have this one. And this one will convert to 0, right? Because inverse one is exogenous to error term. And we can calculate this one. This one is simply sigma epsilon square. And then it is variance on investment. Okay? And then this is covariance between investment and error term. So again it's 0. And it's the epsilon square. So it means this one will be greater than beta. Likely to be greater than beta. Of course, we have to assume that, I mean, it doesn't always hold, it depends on the equation, but our intuition is that beta is between 0 and 1, right? Okay, let's go to our regression, our structural regression. So, beta is what? It's is sensitivity of our consumption on the income, right? So, our intuition says that beta should be between 0 and 1, right? If it is less than 1, what happens? If beta is less than 1, which means that if we make more money, then suddenly we reduce our consumption. That does not make sense, right? If we make more money, we spend more. And if beta is greater than 1, what happens? So if our wage increased by $1 million, then we spend more than $1 million. That is not true, right? So beta is likely to be between 0 and 1. Therefore, if we run regression and estimate beta, and beta, given that beta is between 0 and 1, beta is likely to be exaggerated, where estimate of beta is likely to be exaggerated. Actually, it is very intuitively obvious. Okay, so our OLS estimate should be estimated overemphasized, overestimate coefficients. So, can anyone tell me intuition why we simply run regression about this and ignore this one? Why do you think this beta is actually greater than the true beta? So if we just ignore this and run regression of this, basically we are ignoring the interaction effect, right? So y affects c and c affects y equals c affects y. Right? So if we simply run the regression, then this beta will include all these interaction effects, right? But we don't want to estimate the interaction effects, right? We simply want to estimate this this one way relationship, right? So that one-way relationship should be smaller than the coefficient that takes into account all the interaction. Therefore, whereas beta will exaggerate the true beta in this case. Explore true beta are not correlated. Therefore, our awareness estimate on the INS should be consistent estimate. Okay, let's take a break.